Hi and Assalamualaikum. Today Alisa Syarafana binti AZMIMURAD will do a presentation about the experiment in microwave optics. So the first experiment is about the refraction through prism. The objective of this experiment is to determine the refractive index of glass prism. So firstly, uh, refraction is the change of direction of wave passing from one medium to another. So a wave is refracted when there is a change in wave speed and the direction of wave propagation that is related to the direction of change in speed. So this follows the law of refraction, which is the Snell's law, which is n1 sine theta 1 equals to n2 sine theta 2, which is n1 and n2 is the refractive index, which is the theta 1, and theta 2 is the angle of incidence and angle of refraction respectively. So the Snell's law also indicates the ratio of the wave speed uh, in vacuum and materials that equals to the ratio of sines of and incidence and refraction angles that equivalently also equals to the indices of refraction. So the equipment needed for this experiment is goniometer, transmitter, receiver, rotating table, protector, ethafoam, and ethafoam mold, prism mold with styrene pellet. So what we have to do in this experiment, we have to arrange the equipment in just as shown in the figure. So the empty prism mold was rotated, and the prism mold was filled with the styrene pellet. So the movable arm of the goniometer was rotated, and the angle was located at which the refracted signal is a maximum. So from that we can know the incidence angle and the refracted angle using a protector, which is the theta 1 and the theta 2. So from the value of theta 1 and theta 2 we can find the index of refraction using the Snell's law. The second experiment is about Lloyd's mirror. So the objective of this experiment is to determine the values of wavelength of the microwave radiation for experiments of Lloyd's mirror. So firstly, Lloyd's mirror is used to produce two source interference patterns that have produced by laser light passing through two slits. So light from a monochromatic slit source reflects from a glass surface at a small angle. So the reflected light interferes with the direct light from the source that will result in forming the interference fringes. So that is the diagram for the Lloyd's mirror. So an electromagnetic wave from point source A is detected as point source C. So the wave is propagated directly between point A and C, but the wave also propagate um, at point B, but reaches at the point C. So a maximum signal will be detected when the two waves reach the detector in phase. So how to know the wavelength of the microwave? So we can know that the distance of the microwave travel of the first minima plus the wavelength is equal to the distance or travel of the new minima. So the equipment needed for this experiment is transmitter, goniometer, track, component holder, receiver, meter stick, fixed arm assembly, and a reflector. So for this experiment, The equipment also arranged as we can as shown in the figure. So the transmitter and the receiver will be placed as far as possible and in equal distance from the center of the goniometer degree plate, and the horns of the transmitter and receiver was directly facing with each other. So the surface of the reflector is parallel to the axis of the transmitter and receiver horns. So the reflector has been slowly slide away from the degree plate while we're watching the meter on the receiver. So the reflector position has been closest to the degree plate, which produces a minimum meter reading. So next, we can know the value of the distance, which is the h1, the distance between the center of the degree plate and the surface reflector. And then we followed the second steps before, and then we can also know the new distance, which is the h2. After that, the distance between the center of the degree scale and the transmitter diode also we uh, measured. So all the data, which is the H1, H2, and the D1, is used to calculate the wavelength of the microwave radiation. Okay, the third experiment is about the Fabry-Perot interferometer. The objective of this experiment to determine the values of the wavelength of the microwave radiation. Fabry-Perot interferometer is consists with two parallel partial reflector, which is the partial reflector is positioned between the wave source and the detector, just as shown as the figure below. So in Fabry-Perot interferometer, this light splits the beams many times using the mirrored reflectors. So the reflectors is parallel with each other at a distance, and the light reflected at those mirror and reflected back to the screen. So each reflection will add a small difference in length. So it will produce an interference pattern, which is a circular interference pattern. The wavelength of the radiation can be calculated from the formula D equals to n lambda over 2. So the equipment needed is transmitter, goniometer, partial reflector, receiver, and component holder. So as usually, we have to arrange the equipment as shown is in the figure. So the transmitter is plugged in and the receiver controls is adjust for an easily readable signal. So the distance between the partial reflector is adjusted and the relative minima and maxima is observed. So next, the distance between the partial reflector also is adjusted to obtain a minimum meter reading. So the distance between the reflector, which is the D1, is recorded, and then one of the reflector is moved away from slowly from the other while we watching the meter. So the reflector is moved until the meter reading has been passed through at least 10 minima and returned to a maximum. So the number of minima that were traversed and the new distance between the reflectors, which is the D2, is recorded. After that, we can from that data, we can calculate the wavelength of the microwave radiation from the previously formula. So that's all from me. Thank you.